Next speaker is André Vink from actually one of our sponsors, MRV. And he's going to talk about high-speed optical networking and service management. Welcome.
Let's see. Yes. Thank you. And actually, up front, I think I have to make some apologies because, well, being a vendor, my commercial counterpart almost begged me on his bare knees to add some commercial slides as well, some product slides. But be aware, I will mention them on beforehand, so you know that there are some commercial slides as well. Well, let me introduce myself. André Vink. I'm in MRV for about 8 years now, and working in both the carrier Ethernet as well as the optical space. And I want to talk to you a little about need for speed or high-speed networking. 100 gig is becoming, well, I would say almost say commodity in the data center space, in the transport space, and also in the markets where we more and more see the 40 gigs. Let's say Cisco ACI, which interconnects on 40 gig. Well, 40 gig interfaces on long haul, or at least longer than your data center, is problematic. So we used to see some multiplexing there, where we do, let's say, 2 times 40 gig and some 10 gigs over 100 gig to make it at least usable to have multiple data centers interconnect and still have your network stretched and shown as a single entity. Bandwidth requirements are growing and faster and increasingly faster, and we see demands of 200 gig, 400 gig. And for now, 400 gig more or less is proprietary. And as MRV, we do not want to go in this proprietary thing. It takes a lot of investment, and probably half a year later, the products are developed that much that they're almost off the shelf. So we prefer to use optics that are on the shelf, but we're trying to run in front. So if the optic appears on the shelf, we take it and you can have it. For the 100 and the 200 gig, or at least the 200 gig, it means that we now have optics that do both. So let's say you have the 100 gig optic and the 200 gig optic, and it's just a question of using the right modulation technique. So QPSK gives you 100 gig, and go to QAM, 16 QAM gives you 200 gig. And these are optics that, well, do around, let's say, 600 to 2,000 kilometers. That's the regular distance. But sometimes you only have a short stretch. You still don't want to do it a single wavelength. And that's 100 gig. So there's another optic called PAM4, which is 100 gig, short distance, 80 kilometers. Still usable, but a little bit more affordable. So for those people that are long enough in the IT market, I would say grab a cup of coffee, because the next 4 or 5 slides is what we've already learned in the modem technique. If you know the 120 kilobit modems to 300 kilobit modems, going to the 50K6 modems, it's all using the same modulation techniques as we currently use in the optical space. So let's say QPSK. It's a phase shift modulation where we use 2 bits per symbol. Many people don't know the difference between a bit rate and a baud rate. For this presentation, I deliberately used a symbol rate, which actually is the baud rate. The baud is the number of bits that you transmit in a single pulse or in a single entity. So in this case, I here say 1 baud, which actually is the same as 1 symbol. So going for QPSK modulation, we have 4 phases, and each phase can send 1 symbol or 2 bits. which means that actually when I do 100 gig, I do 4 phases, so every phase is 25 gig. That's easy. And it would be nice if we could do that indefinitely. So we change the number of phases and go to 8 PSK or DP QPSK, which is actually the same. So instead of using 4 phases, we're using 8 phases. By 8 phases, we have a shift of 45 degrees instead of 90 degrees. And means that we have 8 phases to the power of 3. It means
I have a question. Go back one slide. You're actually to do 100 gig, you're using 2 polarizations and that baud rate.
I'm trying to explain the way of the polarization. This is
But
not exactly.
your math doesn't work out because you can't encode 4 in 2.
Exactly. You're right. You're right. took the wrong drawing. I'm sorry, but the way that this is still valid. This one isn't valid. You're right. This one is still valid. We're using 4 phases, and each phase sends 2 bits. The same we can do for 8. And for 8, so we have more shifts, which means that for 8 PSK or DP QPSK, we can do around 150 gigabits. But it's becoming harder and harder to discriminate all these. So it's a little bit difficult to go to 16 PSK. So what the market came up with is quadrature amplitude modulation, which actually is a combination of phase shift modulation and amplitude shift modulation, or AM. This means that you can have different phases and different amplitudes. So you can multiply them, and it gives you numerous variations. 4 QAM, 8 QAM, 16 QAM, and all differ on the way or the number of bits that you can transmit. So go to 16 QAM. You can have 3 amplitudes and 12 phases, or you can have 4 amplitudes and 8 phases, or 2 amplitudes and 8 phases. It's all 16 QAM. So based on a lot of testing, IQT decided that the best way to do it is 3 amplitudes, 12 phases, giving you 25 gigs symbol rate in a 200 gig transmission rate or line rate. And here you can see that you both have a phase shift and an amplitude shift. So now the decision, 8 QAM or 16 QAM. And it very much is depending on the DSP that is used. The current DSPs that are on the market are capable of doing about 30 G symbols of processing. That means that, but they are quite susceptible to OSNR. It means that on 16 QAM you have a limited reach of distance. You talk about 1,000 kilometers compared to DP QPSK, where you can run also up to 2,000 kilometers. So it means it makes about half of the distance, and it requires some more electrical power. Future DSPs, actually it's almost on the market, capable of doing 45 to 50 G symbols, means that we can use 8 QAM. 8 QAM instead of 4 bits here, we're using 3 bits here. Less susceptible to OSNR, so we can have a longer distance that we can reach. Current digital CFP2, in the presentation, previous presentation, it was already mentioned. There we saw the board with the DSP on the board, and you had a CFP2 which only had the laser and some logic in it. In the digital CFP2, the DSP itself is already on board. It's in the optic. Current optics are capable of doing DP QPSK, 16 QAM, and several also using 8 QAM already. Few words on spectral efficiency, because that's what you really want. You want to have at least as much waves that you can use in your WDM system. So let's take a 100 gig wave. That means if you have a 200 gig demand, you're using 2 waves. It requires 2 waves at 100 gig. If you're using 200 gig, you may need an extra a transponder, or may do some extra amplification, because the 200 gig can do less distance than the 100 gig currently. But on spectral efficiency, it's much more, because you have 100% more waves that you can use on 200 gig. So both in a 50 gigahertz grid, you can reach the double number of wavelengths and doing extra speed. If you combine that with a flex grid ROADM, which means that you, instead of using a fixed grid and say, okay, every channel has 50 gigahertz spacing or 100 gigahertz spacing, you use a spacing of, let's say, 12.5 gigahertz. That means that we can do a 50 gigahertz spacing or 62.5 gigahertz spacing, 100 gigahertz spacing, just depending on the spacing you require. Let's go for a 400 gig wavelength will not fit in a 50 gigahertz spacing. We're probably going to 62.5. So if you make that flexible, you can fill up your waves as efficient as possible in your ROADM. A little bit about the shortwave optic, so up to 80 kilometers. It's PAM4, or phase amplitude, pulse amplitude modulation. This is what an optic usually sees. This is a 1, this is a 0, and you have the difference between them on the bits. Instead of using on-off keying, it's something that we already did in a 10 gig optic. 10 gig optic is nothing more than on-off keying. There's light or there's no light. We use several amplitude heights. And the combination of that with the modulation means that instead of one eye, you have several eyes on the same fiber. It also makes the eye a lot smaller. So it's much more sensitive to OSNR. It's much more difficult to find, is this a 0 or is it a 1? Is it a 0 from this eye or is it a 1 from that eye? It's a little bit more difficult. So the distance that you can run with such an optic is less. However, since the optic is some cheaper, and not all data centers are 2,000 kilometers away. Maybe you have just a data center and another one on 30, 40 kilometers. This is a perfect optic, still doing one single wave, but not per se a coherent optic with DP QPSK or QAM. So a few slides on the portfolio from MRV. What are we doing now and what's coming on a very, very short term? First one is moving from the current CFP, which is an optic which is almost as big as your hand, to the CFP2, more like an XFP size. QSFP on the access side, OptiDriver, the optical portfolio from MRV, will release the single transponder, which means 100 gig access and 100 gig trunk. Fits in all chassis, and it makes it possible to have 48 times 100 gig in a single chassis. But since we have the optic, the CFP2, that's capable of doing 100 gig and 200 gig, there will be another transponder as well that do 2 times 100 gig in a 200 gig. Same principle, just time division modulation on 100 gig. combined with the CFP2 that is capable of doing DP QPSK for 100 gig, 16 QAM for 200 gig, or 8 QAM for 200 gig. Uses OTN on the outside, OTN with FAC information. So actually the line rate for 100 gig will be about 111 gig, and for 200 gig it will be around 220 gig for on the line rate side. Here the same module, but since the largest chassis from MRV is three of these units high, we said, okay, let's combine it, and let's have 3 of these modules on the single blade. That means that we can have 72 times 100 gig in a single chassis, and that makes it quite high dense. It's quite 16 of these modules in a single chassis of, let's say, what is it, 9 RU. It is encryption ready. It means that we will not have the encryption when we release this board. However, all the chipsets that are on the board are encryption ready. That means that if we release the software, all the 100 gigs and the 200 gigs will be encrypted as well. So on the largest chassis, you can have 16 of these boards inside. But if you want to have much more like pizza box like side, this is one that actually can fit one inside and gives you a pizza box deployment with 6 times 100 gig in 1 RU. So let's say you have something like that implemented. Then you really would like to manage it, especially if it's not only a point-to-point, but the network is a little bit larger. You want to have actually a large, nice GUI that you can work on. You want to have auto-provisioning. You want to have measurement on your optical layer as well. You really would like to see how your optical layer is working. So you would like to, probably would like to see where are my transponders, where are my chassis located. Are all my links that are running on this on these networks are all running fine, or is there one that has a problem? Who do I need to inform if there is a problem? Are there specific links that are more important than other ones? Do I need to alarm a specific person, or is it just enough to raise an alarm? All these things you would like to know and you would like to control. And this is a little bit different from a switching environment. In a switching environment where you have an electronic backplane, there's probably some kind of switching fabric or multiple switching fabrics on your backplane that will interconnect all the switching modules that are on the line cards itself to interconnect all these flows. Well, in optical, it's a little bit different. You don't want to have an optical backplane, because if you have an optical backplane, or at least if you have a backplane, it's by default, somehow you will run into problems where are in bandwidth limitations. So actually, what we do is connecting everything on the front. So the box itself is only passive. It gives you some management information, several management buses inside, but there's no data flowing on the front, on the back of the chassis. That means that you have to interconnect on the front once and for all the connections between your transponders and your muxers, between your transponders and your ROADMs, whatever. So at least you have to know which connection, what is connected to what physically, and then the system will draw it the rest fully automated. It also goes for the ROADM automatic provisioning. It's automatic discovery. What is connected to what? Wavelengths do I have? What is the network topology? And the nice thing is, if we know that, we can have a point-and-click auto-provisioning. Just click here, just click there, and let's see what is the best connection between these points. What are all the optical levels? Do I need to recalculate some optical levels? You don't want to do that by hand. You want to have the system just here a click, there a click, and okay, the service is provisioned. But not only the service is provisioned, but also the monitoring is provisioned. And also the alarming is provisioned. It's just to say, if I think the alarm is more important than from other services, I can raise that alarm or raise the importance of that alarm. So that's what's shown here, just some point and clicks, and the ROADM itself will configure the ROADMs, will configure all the wavelengths, will configure the monitoring for all your optical services. And if you have done that, then it means clicking your service, and it will show you all components end-to-end in that service. It will show you if all components are running fine. If there are amplifiers in between, if there are dispersion compensations modules in between, all these things are shown in the diagram and are controlled from the system itself to make sure that all wavelengths are running optimally. That also goes for optical channel monitoring. You would like to see, at least if you are looking at the network and you have a problem, you would like to see if there was any power drop on the link. So all links are measured continuously for its power output and its power input on all waves. So if there is any problem at any time, you can go back in your screens and say, okay, this is where the problem was. Oh, it was an outage, someone broke the fiber. There is an optic that's maybe not completely okay, so I have to remove that one. All these kinds are done by optical channel monitoring. Same goes for frequency drift on the channel, OSNR showing on the optic, so you can see all the optical values in your monitoring system as well. So from that aspect, ProVision is both an optical provisioning and monitoring system, as well as a carrier Ethernet monitoring system. As I mentioned before, MRV is working both in the optical space as well as in the carrier Ethernet space. We do the same for the carrier Ethernet in the same platform, which actually means that if you have a connection that goes from one carrier Ethernet point, one entrance point to another entrance point, and I want to have a connection between that, and there's an optical layer in between, it will provision both the carrier Ethernet part and the optical part, and gives you a carrier Ethernet service end-to-end, and then you can add Y1564 service turn-up. You can create birth certificates. You can have OAM checks end-to-end between the carrier Ethernet layer as well. So it will check the optical service and it will check your carrier Ethernet service. All from one service provisioning and controlling application. So in this case, then it becomes a plan activate monitoring system where you also have your troubleshoot information and your maintenance information. And service turn-up and tear-down is becoming quite easy. It's just pointing and clicking for a single service or for multiple services. And that brings me at the end of my presentation on both the optical part and the carrier Ethernet part on the MRV OptiSwitch and ProVision. A few customers where we already installed these things. A lot of service providers, hospitals, well, a lot of names in the Benelux. I'm working on the Benelux and the Nordics, but also here are some Nordic partners as well. Any questions?
Hi, Frederick from Sunet Nordnet. So a few pretty easy questions. So there was nothing about netconf Yang in this slide. So where's the support?
Where's the support? On the carry Ethernet part.
I don't care about carry
But
Ethernet.
you wanted to know on the optical part. Well, on the optical part, for now it's mainly on the ROADM side, where it's much easier to request the configuring of a ROADM with a netconf and Yang model instead of doing SNMP and requesting all this information by SNMP. So for now it's not fully implemented on the optical side as well. As you mentioned this in your presentation, the optical vendors are a little bit behind on the implementation of netconf in their optical platforms.
Yeah, a little bit. Could say that. So another question. So who is building your CFP2 DCO? Because if someone buys this kind of thing, you probably want them to speak to other things that's not MRV. So does it do high gain FEC in 100 gig mode?
I'm sorry?
The CFP2 DCO
Yes.
that you're relying on for the optic driver 200 gig transponder, or
Yes.
max spawner actually. Who is building that optic? I presume it's not you, it's probably someone else.
It's not us, although we used to have an optical or a part of our business was building optics itself. We sold that several years ago. Now we have two vendors for the optics. However, for the CFPs, I don't exactly know by heart now who builds them.
All right, but does it speak any protocol that I could speak, for example, to my Juniper routers or my Huawei routers or my Alcatel routers? Or do I need to have an optic driver on the other side of the line as well?
Not per se. We, as MRV say, we only work standards based. However, it really needs testing because everyone says I am compatible. However, sometimes some adaptation is needed. But we always say if it would not be compatible, we will certainly try to make it compatible because a lot of things are just a requirement to tune, and it's not per se a protocol problem. It's more an implementation problem, so then we can change that.
All right, yeah, that's everything I got, but I think it could be a good tip that no one wants to point and click anymore. We kind of want computers to program the networks, not people, so point and clicky things, no one cares. I mean, probably some people care, but...
Well, it depends. MRV is for a large part working in the data center interconnect space, and there it is looking at transport networks. It's a bit different. However, we are for a large part also doing the data center interconnect and enterprise networks, and on this space it's largely a single entity network, a single vendor network, and then point of click is certainly a big plus for these customers.
All right, I think that's everything for me.
So I have a question. So if you want your router to move traffic away when your link is starting to get bad, the OTN side of your line system has a signal degrading indicator that you can set the threshold level for. Like you can say, I want 2.5 dB OSNR, and once it goes past that, you get signal degrade. How do I get signal degrade from your transponder to the attached router over that client interface fast enough in your configuration?
Currently, we do not implement these things because, as I said, we are moving largely in the data center interconnect space, which are point-to-point networks, either or rings with only a few ROADM nodes. So that's a little bit a different situation. When you're dealing with these kind of things, you usually have transport networks, and that's a little bit the space. We are working more and more in this part of the network. However, we did not implement that yet. no more questions in that case, then I'll finish my presentation here.